Okay, so we would be discussing the problems of AtCoder beginner context 361. The problems that we would be discussing are A, B, C, and problem E. So let us start with problem A. So problem A was a pretty straightforward problem. The statement goes like this: you are given an integer sequence A of length n and integers k and x. Print the integer sequence B obtained by inserting the integer x immediately after the kth element of it. So we are given an integer sequence A of length n, and we just need to insert x at the kth after the kth elements of A. So what we can do is we start printing the elements of A, and after the kth element we can just print x and then print the remaining elements of A. If we look at the sample input, we have been given integer sequence 2, 3, 5, and 11, and we need to print 7 after the third element. So we have 2, 3, 5, and then we have 7, and then the remaining 11. The implementation is also pretty simple. First, we need to input the values n, k, and x, and then the element of the array. And while printing, we just need to check whether the position of the element is k, and then we can output just x and then print the remaining elements of the array. With that, we are done with the problem first. Now let us move to the problem B. The problem B is intersection of cuboids. In a three-dimensional space, let C, A, B, C, D, E, F denote the cuboid with a diagonal connecting A, B, C, and D, E, F. So what they are saying is basically, suppose this is one face of the cuboid, and this is the another face of the cuboid, and then we have this diagonal connecting the different points. Then this is the point A, B, C, and this is the point D, E, and F. With all faces parallel to the xy, yz, and zx plane, given two cuboids C with coordinates A, B, C, D, E, F, and C with coordinate G, H, I, J, K, L, determine whether their intersection has a positive volume. So we have been given two cuboids in this fraction with the coordinates of the diagonals, and we need to just determine whether when they intersect, whether there is a common area of intersection, or whether they overlap or they do not overlap. So let us first look at a sample input that has been given in the question. Okay, so this is the figure that has been given for sample input. So this is the point that has been mentioned as ABC. This is A, B, C, and then this is the point is D, E, F. Similarly, we have this point as G, H, I, and this is the point as J, K, and L. Okay. So the common area of intersection is this, as we can see. Now, one common observation is that in order for these two cuboids to intersect, then they must overlap in all the three directions. For example, let us see for these two particular cuboids, this is the area of overlap in the x direction, this is the area of overlap in the y direction, and this is the area of overlap in the z direction. If it does not overlap in either of these three directions, then the intersection of these two cuboids will not take place. What I mean to say is that suppose these two cuboids are intersecting in x and y plane, but if this cuboid has passed somewhere above the first cuboid, then there would be no intersection. So what we need to just check is whether they are intersecting in all the three directions or not. For that, let us first focus in the x direction. Suppose this is the x direction. Then what are the all the possible ways for these two cuboids to overlap? This is the point end point of the diagonal for the first cuboid A and D. Then they can overlap if the cuboid or the second cuboid passes like this. This is G and this is J, or this is G, this is J, and this is A, and this is D. Another case is if the first cuboid lies entirely inside the second. This is A, this is D, this is G, and this is J. Or the other case, like this is G, this is J, this is A, and this is D. In either of these four cases, there will be an intersection in the x direction. Similarly, we need to check for other direction like y and z, and if it overlaps in all the three directions, then we can say that yes, there would be a positive intersection of the two cuboids. Let us check the implementation. Okay. So first I have taken the parameters A, B, C, D, E, F up till L, which represent the endpoints of the coordinate. This is the first cuboid and this is the second cuboid. Now, these are three variables x, y, and z, which respectively denote the overlap in the respective direction. Now, to check the overlap in the x direction, as we have so seen the four cases above, either this particular case or this one, or the remaining two cases in which the one cuboid lie inside, entirely inside the other is true, then we can say that yes, they are overlapping in the x direction. Similar is the case with y direction and z direction. Now, if they are overlapping in all the three directions, then we can say this is the positive intersection. Yeah, otherwise, no. So I hope this question was clear. Now let us move to the third problem. Okay, make them narrow. So the problem statement goes like this: you are given an integer sequence A of length n. Freely choose k elements from A and remove them. Then concatenate the remaining elements in the original order to form a new sequence B. Find the minimum possible value of this. The maximum value of B minus the minimum value of B. Okay. So we have been given an integer sequence of length n. What we can do is we can pick any k elements and remove from this. And then we need to print the value of A max minus A min. And what we need to achieve is we need to minimize it. Let us look at one of the sample input. Okay. So this is the array 315549. Suppose in this case we remove this particular element 1 and 9, then the remaining array would be 3, 5 and 4, and the minimum minus maximum would be 2, which is 5 minus 3. Okay. So one common observation in such type of question where we are required to print the value of A max and minus A min is to first sort the array. So let us say we sort the array, and the sorted array is like this: A0, A1, all the way up till A. Now suppose initially we do not have any element to remove. Suppose we are not given the option to remove the element. Then the answer would be surely an minus a0 if this is the sorted array, right? Now if we are given the option to remove k elements, and suppose we remove this element a0, a1, a2, a3. Suppose we are given the option to remove k elements and we remove these elements like a1, a2 and some remaining middle elements. So will this help us? Definitely not, because the minimum still remains a0 and the maximum is still an. So one thing is clear: if we have the liberty to remove k and ak elements, then this k element should be either from the beginning or from the end. Now, since we can remove k elements, each of the starting k elements can become a minimum of the array. For example, this is a0, a1. Suppose we can remove two elements. Then if we remove these two elements, then this particular element can become the minimum of the array. If the value of k is 3, then we can remove starting 3 elements, and this can also become a minimum of the array. So what we can do is we can iterate over the minima of the remaining array and then check what is the answer if that particular element is made the minimum of the new array. So let us see. If this is our given array A0, A1, A2, A3 in the sorted form, and suppose out of k elements we have removed x elements from the beginning, then we can remove k minus x elements from the end and check whether the given maxima minus minima is minimizing our answer. Okay, so now let us move to the implementation. Okay. So first we are taking the input n, k and the elements of the array. Then as mentioned, we need to sort the array. Then first initially we are initializing our answer we will with int max. Now here we are iterating over the minima of the array that we can achieve after removing the starting I elements. Suppose if we remove I element from starting, then we can remove k minus I remaining element from the end. So this stamp indicates nothing but the number of elements that we are removing from the end. So if we are removing temp element from the end, then the index of the maximum remaining element would be n minus 1 minus temp. So this j denotes the index of the maximum element that is remaining after removing temp element from the end. And then we will compare it with our currently calculated answer, and aj minus ai, which is aj means maximum and ai means minimum. So here it is our final answer. So I hope this question is also clear. Now let us move to the problem E. Okay. So problem E is tree and Hamilton path 2. In the nation of AtCoder, there are n cities numbered from 1 to n and n minus 1 roads numbered from 1 to n minus 1. Road I connects cities AI and BI bidirectionally and its length is CI. Any pair of cities can be reached from each other by traveling through some roads. Find the minimum travel distance required to travel to start from a city and visit all cities at least once using the roads. Okay, so what we have been given is a weighted tree, and we are asked to calculate the minimum path such that we start at any given particular vertex and travel each vertex at least once. Okay, so let us have a look at a given sample input. So this is one sample input that we have been given. The vertex one have been connected with 4 with weight 4, with 2 with weight 2, and 3 with weight 3. Okay. So if we start in this case, we start at particular vertex 4, then our cost over path would be, first we will go here, it would be 4 plus here 2, and then again come back 2 plus, and then go in this direction 3, which would be 11. Okay, so this is our answer for this particular case. Now the first question that comes to our mind is, uh, does our answer depends on the starting vertex? What we have been asked to calculate, we have been asked to calculate the minimum cost of the path such that if we start a particular vertex and travel all the other vertices at least one. So does our answer depend on the starting path? Let us check. Okay, so in this particular case, if we starting at this vertex, then we would first go here, then go here, then here, then here, come back, then here, here, and here. Okay, but instead of this, if we would have started at a different vertex, let me erase it. Let's say if we would have started this particular vertex, then we would have gone here, and we need to just come back here and end here. Then the length of this much path would be relaxed as compared to the earlier one. So it clearly means that the answer depends on the starting vertex. One common intuition suggests that it would be better if we start at a leaf node. Let us see how. Suppose we have a tree like this. If we start at this vertex, go in this particular direction, come back, and then go here, then we would add the length of this particular path twice. But instead of this, if we start at a leaf node, let's say this one, then we would need to go in this direction only once, and the path would be added only once. So it is clear that it is beneficial to start at a leaf node. The first observation is it is beneficial to start at a leaf node. But there may be more than one leaf node. Which one would give us the maximum benefit? To check this, let us look at a slightly different problem. Suppose instead of this, we have the problem that if we have a tree, okay, then we need to, suppose we have a slightly different problem that we need to start at any particular vertex of the tree, visit each vertex of the tree, and then come back to the starting vertex. Okay, so let us check. If we start at this particular vertex, then we would go here, visit this particular branch, come back, go to here, return back, go here, go this direction, come back, go here, come back, and then go here. What we can observe is that we are visiting each edge of the tree twice. Right? Let's say if we start at a different vertex, let's say instead of this, if we start at a different vertex, suppose we started from this particular vertex, then we would go here in this direction, here, come back, go in this branch, come back, go here, come back, here, 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 come back. Okay. If we start at a different vertex, then again we are, uh, then also the total cost of the path would be twice of the sum of the all the edges, because we are visiting each edge twice. So this gives us the observation that if the problem has been different, that we need to return back to the starting vertex, then the dependency on the starting vertex gets removed because we are adding each edge twice. Now, if we return to our original problem, where we have been given the question to end at any particular vertex, and we need to visit each vertex once. Let us visit to the original problem. Suppose we start from here. Had we If we had to end on the starting vertex, then we needed to end the each edge twice, and in that case our answer would have been the sum of all the edges multiplied by 2. But since we have the liberty to end at any vertex, we can relax a given length of the path. For example, we go here, come back, go here, go here, go here, then this much length would be added twice, no change in that. But if we go here and end our journey here, then there is no need to add this particular path twice. We need to end it only once because we are ending it here. It means that we are relaxing this much length of a path in our answer. So what does this mean? It means that our aim should be to relax as much maximum length as we can, because that would give us the maximum benefit. So as we can see here, if we can observe, this is the maximum length of the path which have a maximum distance. If we can relax this particular edge anyhow, it would give us maximum benefit. So the question now gets reduced from to finding two vertices in the tree which have a maximum distance from one another, which is nothing but the diameter of the tree. So what we need to do now is that we need to find the diameter of the tree and subtract it from our original answer, which is nothing but the sum of all the edges multiplied by 2. Why? Because we can relax a particular length of the path and we want to maximize the relaxation. So it should be the maximum length, which is nothing but diameter. So now let us move to the implementation. First, we have taken the input for n. This is the adjacency list representation for the tree. We are just inserting the adjacency list. Now here we are calculating the initial answer, which is nothing but twice of the sum of all the edges as we discussed above. Now, how to calculate the diameter? The calculation of the diameter is a pretty standard problem. First, we can start at any vertex and find the vertex which is at the maximum distance from it. Suppose we start from this particular vertex and find this vertex to be at a maximum distance from the starting vertex. Then we can start another BFS from this vertex and check which vertex is at the maximum distance from this particular vertex, and it would give us the diameter of the tree. Basically, we would require either two DFS or two BFS. Okay. So, as mentioned, initially we can start from any vertex. Here we are starting with 1, so we will start at 1, and each time we are calculating the distance of every vertex from 1 and comparing it with m, storing the vertex of maximum distance as VER, and starting the second BFS from VER and calculating the maximum distance in m and subtracting it finally from our answer to get the final answer. So this was nothing but the two BFS used to calculate the diameter of the tree. This was a pretty standard problem, and you can find the implementation online also. So I hope this question was also clear.